upon 2, 0 to negative pi upon 2, 0. Okay, that's what I have. I didn't miss anything. Right, so are you looking at a big version of that piece of paper, or do I need to click into it? Big version, good. I would certainly, first thing I would certainly do is figure out what the heck this thing looks like. Well, if I'm doing a cosine function, that's 0, right? And then if you go down to pi upon 2, it's here, right? And if you go down to negative pi upon 2, it's here. You could certainly do that on your calculator if you weren't sure. And it looks like you're going from this point, going that orientation to this point, and then you're going from here all the way along to there. So this whole description is basically this fella, right? So the guy that we call D, which is the internal area, is basically the internal part of this dome shape. So that wasn't too bad. It brings up, I think, Natalie's point of view. Do you recognise that the orientation here is clockwise? What is the only minor change I need to do to make sure my integral works?
Put a negative in front of it?
Stick in a negative, right? Because you get, I don't know the answer yet, but if you get 5, it means it should be negative 5, right? Or vice versa. So we'll bear that in mind. Now, in this question here, would that be P and this will be Q? Right, agreed? So if P is equal to e to the negative x plus y squared, its partial derivative with respect to y is just 2y. Q, on the other hand, is this fella. And the partial derivative of this guy with respect to x equals 2x. Nothing looking good? So that fella there, just pause a little minute. Have you noticed that sometimes they do this guy like this, and sometimes you'll see in textbook this little circle around it? Have you noticed that sometimes if you're looking up other places? This is the same thing as that. Do you know that the notation is just, this is an emphasis, but it's a closed loop, right? That you start and finish at the same point. This is a more general version. This could be any line curve, right? Could be any, but this one is a specific one. So I guess technically all these questions should be this one, right? But moving on. It's a double integral with a negative in the front because of the orientation issue. And this fella, take away this guy, and I'm going to call it dA. I find it safer to do dA because if I say dx dy, won't it end up being dy by dx? Right, because it just is. So if I leave it as dA, I can figure that out later. Another question. Do you like my new thingy, Bob? Is the picture cleaner or different, or is it just the same as my camera version?
I think it looks a little bit cleaner.
A little bit cleaner. I'll do. And I hope I don't. This will reduce me getting that bandwidth issue, because it might have been a problem with me having two things connected to Zoom from the same place. So that particular fella is going to come out as negative a double integral of 2x take away 2y dA. And if I go back to my picture, we have to decide the integral's boundary points. I think this is a good candidate, isn't it, for vertical rectangle? And if I do a vertical rectangle, won't the x's be between negative pi upon 2 and positive pi upon 2? And the y's will be from the bottom, where the y value is 0, to here, which is cosine x. Are you happy about the boundaries that I've just set up? I like this new camera, because that red looks red. everything kind of blended into less distinction. So I think it's working good. I'm pleased. So our double integral is now from x equals negative pi upon 2 to x equals positive pi upon 2 of the integral of y equals 0 to y equals the cosine of x. 2x take away 2y. Since these are first, you do the dy first and the dx second. In fact, I think the vast majority of questions, don't they end up being dy by dx? You know, the y's are the first integral and the x's are the second. So this is negative this fella to here. If you integrate this with respect to y, you get 2xy, take away y squared, evaluated at these boundary points. Okay, so what's that going to get me? It's going to get me 2x cosine x, take away cosine squared x, subtract a whole load of nothings. I think I'm going to finish at this point. In other words, I'm not going to do any more of the question, but I do want to talk about how you would integrate each of these pieces. You've got this piece that you need to integrate, and you've got this piece that you need to integrate. Now, you can either split them into two separate integrals and then do what you need to do, which probably would be a good idea here. So let's look at each one separately then. Don't need the details, but how would you integrate that? What's the process you would use?
Integration by parts.
Correct. And wouldn't f be 2x and the g would be cosine x? Unless you do the udv version of that. Now, this piece. I guess you could stick a negative in there. Can't really integrate cos squared x. A u sub won't help you. Integration by parts won't help you. Trig identity will help you. So if you ever thought that you didn't need to remember your trig identities, you're sorely wrong. You do. Can you remember what cos squared x can be turned into that helps you integrate it? I know you can turn into lots of things, but only one thing will help you to integrate it.
1/2 plus cosine beta over 2.
Well, in this case, x's, but yes. Agreed? Now, that is a Calc 2 question, right? So that's still got a bit of work in it. This is another Calc 2 question. And I do this answer and I take away that answer, and I know I don't, but pretend I got 42, just for argument's sake. Do you know what I've done wrong? I forgot all about that guy. It's easy to lose track of that guy when you split something into two parts. At least it is easy for me to forget it. And what you do is you get this answer, take away that answer, and you get your thing, and you think, hey, great, and then it says wrong. Isn't it the negative of whatever that is? So the answer would have been, in this case, negative 42. And if it was negative 4, it would have been plus 4. Natalie, you said you've done this one? Yeah. You'd have a great memory. Do you remember what the answer was?
Pi over 2.
Oh, pi over 2. So a much nicer answer than 42, but I like 42 because it's a kind of cool number. Interesting because of how much work there was still to do in it. So I was quite happy with picking that one.
Yeah, I guess one thing that I'm kind of confused about is like a lot when I was reading like the textbook and stuff and like watching the videos, they keep talking about like whether like C is like a positive oriented curve or like a negative oriented, and like how do we know when to put the negative sign in front and stuff?
Let me show you this one and tell you how I how I decided if it was positive or negative. The first part is easy. When you go round the curve, if you go round in a clockwise direction, we call that a negative orientation. So that's why there was a negative stuck in our integral. If you go round the curve in a counterclockwise direction, then that is called positive orientation. So the question was, well, how do I know which I've got? When they describe the curve, try and draw it the way they're describing it. I'll show it on me. Suppose we have a curve and it's a classic triangle. You know they love triangles, right? Let's say you're doing a curve that was a classic triangle. And they went and said it went from 1, 2 to 4, 0 to 0, 0. And then it went, I hope that's a triangle, by the way. And then back to 1, 2, right? So can you imagine that's the pathway that C is? So I draw my little guy and I go 1, 2. And then I go to 4, 0. And then I go to the origin. And then lastly, I go back. But notice the order. I went from here to here to here to there. Can you see that I can now see that that is definitely a clockwise pathway that I followed?
Yeah.
Right, from one, so that one is clockwise, and clockwise is negative orientation. So that means stick a negative in front of your Green's theorem formula. That help?
Yeah, that makes a lot more sense now.
Right. So I like pictures anyway because I'm visual, but I think you need to do pictures in these things. Even the simpler ones can sometimes catch you out on orientation, if nothing else. Because you draw it and it's a little triangle, you think you know what's going on, but you find out later that it was going the wrong direction, and so your answer is negative something instead of positive. So I was about to do this fella, right. I remember, did we do 9? I think we did 9 last time, didn't we? I got a feeling we did. I'm trying to find a triple one. That is surprising. Oh, there wouldn't be. I'm talking line integrals. Of course there wouldn't be. There isn't a triple integral for Green's theorem. That's silly. There's another guy who does that, but it's not Green. Okay, is there any in this bunch that you want me to go over or to deal with, or whatever the word is?
Something that's kind of been confusing to me the whole time is when they ask for the inertia. Like, how do you know? Because they always ask around the diameter. So, like, which one do you choose?
Oh, so I think I'm looking at an inertia one, this one here, for instance. Do you want me to just go through that one? I think when you're doing inertia questions, it's better if you just take the formula that they give you and say, okay, this is the inertia for this situation, because it just makes life easy. So I of x, the inertia around x, is negative rho over 3. The line integral c of y cubed dx, okay? What do we know about the density function? It's rho, so that's taken care of. What are we doing as a shape? It's a circular disk, which most of these darn things are. A constant density rho and about a diameter. So there's something missing here. Oh, well, I guess it's circular disk. I don't see what the radius of the diameter of this circle is.
It says the radius is A.
Is it? Oh, good. Is it somewhere where I just missed it? Oh, yeah, it's somewhere where I missed it. Now I'm happy. Right, there's my little picture. It's the whole thing, isn't it? We're good. So I'm assuming that they're going to go around this as a simple closed path. And let's go the positive way, right? So we don't make life harder than it already is. So far, so good. Now, this negative rho over 3, I'm just going to forget that one for a while. And let's just focus on this fella. Have you noticed that I've changed the y cubed dx to y cubed dx plus 0 dy? Would you agree that 0 dy is the same thing as y cubed dx? For me to be able to do Green's theorem, right, don't I need a p and a q to work with? Even if it ends up being 0, I still need to have it, you know, to keep the process going. So that makes this fella y cubed, and it makes this fella 0. Are we cool with that? Now, that makes the derivative with respect to y 3y squared, and that makes the derivative with respect to x still 0. Are we cool with that? So our integral, this fella here, I guess I should stick my rho over 3 again, is equal to negative rho over 3, a double integral over some region D, which is basically the whole circle, right? The whole disk. Some region D, this fella. Right, still Green's theorem. Right, let's put all the pieces together. Oh, I'm writing this down. You should tell me. Yeah, I'm writing away quite happily thinking you can see it. Can you see it now? I'll give you a few moments to do that. I'll do my usual cam scanner and put it online. So if you don't want to write all this, you can certainly wait until you see it. Right, be comfortable so far with what's been written there. Okay. Now, if I replace, so I'll rewrite this guy just so I've got something to compare it against. So I'm just rewriting the last line. So we are looking at, well, dq by dx is 0. Take away dp by dy is 3y squared. And I'm just calling this guy d. And you probably don't need anywhere near as many lines as I'm writing down. Are you happy about the negative 3 killing off the negative 1/3 and getting a basically just a row tagged on at the end? Now, to remind you, this is what region D looks like. I would say, and I hope you agree with me, that this question is better done in polar form than in XY form. And isn't dA a holder for XY, dx, dy, and it's also a holder for r, dr, d theta. Now, if I decide to describe this region D using the polar world, you're going to have an r value from 0 to a, which is why I was pausing so much, right? And what we also have, because it's a complete disk, a complete circle, that guy. Agreed? So that now gets me rho, an integral from r equals 0 to r equals 9, and an integral from theta equals 0 to theta equals 2 pi. I'm going to do polar, so remember to put the R in, right? R dr d theta. I'm missing one last piece of the puzzle. Doesn't y squared have to be turned into polar format? And that means you just have to have a good memory. What is y equal to in polar form? I think you're saying it, Rachel, I just can't hear it.
Isn't it r sine theta?
Yes, you are right. Squared. Okay. So we now have this fella. And eventually, that fella. I think this happened as well the last time. Can't we split this into two integrals, one with a dr and the other with a d theta? And computationally, that actually makes your life a little bit easier. So I'm going to do the integral from r equals 0 to r equals a of r cubed dr. And I'm doing the integral from 0 to 2 pi of sine squared theta d theta. We're kind of reaching a natural end point here as far as what I need to do. Would you agree that's just a classic 1/4 r to the 4 power rule? How are you going to deal with sine squared? Got to
Power
integrate.
reduction formula.
Yeah, so you'll call it 1/2 brackets 1 minus the cosine of 2 theta. And hopefully you get a nice answer. I'm going to make an assumption here. If I get Ix, right, this is inertia around x, wouldn't Iy be the same? Just by symmetry.
Yeah, it should be.
And I'm pretty sure it is. So if you want to save some time, as your first estimate, use the same answer as Ix, and if it works, you say great. And if it doesn't, then I guess there's a asymmetric thing going on here that I wasn't aware of, in which case you just go through the whole process with a slightly different formula. And to remind you what that formula was, it was this guy here. Oh, I don't know. One of them has a negative in front of it and the other doesn't. You see how this is a negative thing going on and this doesn't? No, I think it still ends up being the same. Has anybody done question 10? Right, was it the same for both? Yeah, okay, so it is the same. I think the fact that that doesn't have a negative, later on there'll be some two negatives cancelling or everything's positive all the time, in which case that's why it stays the same.
I think the fact that it's a circle is going to hold true because they're both scaled at the same everywhere.
Yeah, everything looks too symmetric not to be true. I agree with you. You know, that y cubed and ix cubed and these two with the change in sign and the fact that it's all circle. Now, if they had changed that, let me do a slightly different story. Everything else is the same, except it's not a whole disk. It's only that side. So can you imagine that the thing you're doing, right, was that guy, right? Only the right-hand side. Everything else virtually would stay exactly the same. Wouldn't the only change be to the limits of integration? Because if this represents the disk D, right, then won't it be an R value from 0 to A, but won't the theta value change? Now, if you want to describe this region, where would you start as your theta and where would you finish?
Negative pi over 2 to pi over 2.
Good. It's so easy to forget that negatives are valid answers in these questions. Right. Now, if I went back to here, right, wouldn't the only change to my answer be negative pi upon 2 to pi upon 2? And I actually kind of know what that one's going to be. Based on just the whole symmetry of the thing, won't one of them, probably this one here, right, the one that's at right angles to the y-axis, won't the y value probably be 0? I'm just doing by symmetry. What will the other guy be? I have no idea what the other guy is, but it'll be something, right? And that would put somewhere roughly about there is where I'd be expecting to see the thing. Does that kind of make sense in the like the oh god, the centroid of a solid shape, right? The same kind of properties are going on. So don't always assume that the answers are the same. I've just created a situation where there will be a definite there'll be a difference between these two results. Mostly because the D shape is not symmetric, or its rephrase isn't a complete circle, which tends to generate a lot more symmetry than parts of circles would. We need another question. Do you want us to go to line integrals? Or did you finish them fine, or you want? Rachel, you look like you were going to say something.
Well, on the last question, I was just wondering, is the radius of A, is that just a placeholder because we don't know what the radius is?
Yeah, and more than just that, because of what the answers are. Natalie, did the answer have an A in it somewhere? I'm assuming it should.
What?
The answer to this question here, right? The IX, did it have an A in its answer?
A like alpha? Yeah.
Yes, A like an A as an apple.